This is Chemistry CP debriefing on a homework assignment called Heat Equation 5 Phase Changes. In this homework assignment, I had provided two examples of how to find the answer. So I'm going to skip those and go directly to showing how to work out the solution to each of the problems that follow those two examples. The first problem states, calculate the heat energy needed to heat 85.0 grams of solid iron from 425 degrees Celsius to a final temperature of 1,538 degrees Celsius in the liquid state. And in parentheses, I said you need to heat it and melt it. The reference table I'm using is the spring semester CP Physics reference sheet that I provided to you students. The substance is solid iron. When I look at this table of information for solid iron, I see its melting point is 1,538 degrees Celsius melting point. And this problem takes place at its melting point at the end. Now it begins far below that temperature, so it begins in the solid state, increases in temperature to its melting point, and finally is melted. If I do a heating curve and say, here's problem one, the heating curve is the constraint that we always have to follow. Substances begin generally as a solid. When you heat them up, they reach a point at which they melt. After they have melted, as you continue adding heat, they increase as a liquid in temperature until they reach their boiling point. Then they undergo a phase change and become a gas. Once they're a gas, you can continue to heat them. This is as far as we concern ourselves in this chemistry CP course. This particular problem begins in the solid state and it ends after it has heated itself up to its melting point and has melted. So it starts here, ends there. This will involve two heat calculations. I'll call the first one Q1, which is the amount of heat needed to raise the temperature of the substance to its melting point. And Q2 is the amount of heat energy needed to actually melt the substance. The total heat needed for this problem is the sum of these two individual calculations. The substance is solid iron. Here's the chemical symbol for iron. In the solid state, the specific heat of solid iron is listed here as 450 joules per kilogram per Kelvin. Now we're going to be working in units of joules per gram. There are 1,000 grams in 1 kilogram. So this is 1,000 times larger in value than we really want to use this year in our calculations. So even though it displays 450, I'm going to divide this by 1,000 and say the specific heat is 0.450 joules per gram. And whether I say it's per Kelvin or per degree Celsius is not going to make a difference because a change of 1 Kelvin is equivalent to a change of 1 degree Celsius. That's different from a change of 1 degree Fahrenheit, which is about 4/9 of one of these. Maybe that's not the best way to show it, but a change of 1 Kelvin is equivalent to a change of 1 Celsius. A change of 1 degree Fahrenheit is only a fraction of a change on a Celsius scale or on a Kelvin scale. Another way of putting it is to say a change of 1 degree Celsius is equivalent to a change of 1.8 degrees on the Fahrenheit scale. So the scales between Fahrenheit, Celsius, and Kelvin are different scales between Fahrenheit and either of these two. Same scale, just a different 0 point between Kelvin and degrees Celsius. So I'm going to write this as joules per gram per degree Celsius. The initial temperature was listed as 425 degrees Celsius. The final temperature after it melts, well, that's the same temperature at which it begins to melt, and that is 1,538 degrees Celsius. I need the change in temperature. So I'm going to subtract 1538 degrees minus 425 degrees C is the number that I'm going to use. I'm starting to get too old to do this in my head, so I'm powering up my calculator, and it says 1,113 degrees Celsius is my change in temperature. The formula that I'm going to use to calculate the increase in heat that I need, energy, is heat energy is equal to the product of the mass times the specific heat times the change in temperature. The mass in this problem was listed as having a value of 85.0 grams. The equation Q is mc delta T. Plugging in all the provided values, it's 85.0 grams times 0.450 joules per gram per degree Celsius times a change in temperature of 1,113 degrees Celsius. My calculator displays a value of 42,572.25. That's a little bit more precise than I am interested in. So I will list this as 42,600 joules to 3 sig figs, good enough for now. This is the amount of heat energy necessary to warm up 85 grams of solid iron from an initial temperature of 425 degrees Celsius to its melting point at 1,538 degrees Celsius. This takes me to this point on the heating curve. Calculation Q2. Now I'm going to melt that quantity of iron. The equation to use is heat energy Q is the product of the mass of the substance times its heat of fusion. For iron, the column labeled heat of fusion is the one that we use. Note the units are joules per kilogram on the reference sheet that I gave you. Looking it up for solid iron, the value is listed as 2.66 times 10 to the fifth joules per kilogram. But once again, we're going to be working in units of joules per gram. There are 1,000 grams in a kilogram. So I should divide this number by 1,000. 1,000 is 10 to the third power. 10 to the fifth divided by 10 to the third is 10 to the second power. 10 to the second power is 100. If I multiply 2.66 times 100, I will be moving the decimal point 2 places to the right, and I get 266. So Q2 equals M delta H fusion is the equation to use. The mass is 85 grams, and the heat of fusion is 266 joules per gram. When I multiply that out, my calculator says 22,610. I'm going to round that to 3 sig figs and call it 22,600 joules. That is the amount of heat energy it takes to melt 85 grams of iron. My last step to answer this question is calculate the total heat energy, the energy to warm up the iron to its melting point, and the energy to actually melt the iron. So the answer, Q, which is the sum of these two individual heat energies, will be 42,600 joules to heat the iron plus 22,600 joules to melt the iron. I get 65,200 joules. Using the Greek prefixes, which I wish you would do whenever appropriate, I would say the answer is 65.2 kilojoules. So there's the answer for problem number 1. Problem number 2. Calculate the heat energy given off by cooling 146 grams of liquid methanol from an initial temperature of 100 degrees Celsius to a final temperature of 0 degrees Celsius. Before you read the hint in parentheses, you should already research it on your own and ask yourself, what are the temperatures for the melting point and the boiling point of methanol? So on this chart, fine methanol, we see its melting point is 98 degrees below 0 Celsius. Its boiling point is 65 degrees Celsius. This problem begins at 100 degrees Celsius. That is above its boiling point. So it's going to begin as a gas. The problem ends at 0 degrees Celsius, which is above its melting point, but it's below its boiling point. So it's going to end as a liquid. All problems must follow the heating curve. So on number 2 here, when we consider the heating curve, substances begin as a solid that warm up, that melt, becoming liquids that can warm up until they boil, then vaporize into a gas, and then you can heat the gas. So we're beginning this problem as a gas, and we're ending this problem as a liquid. Therefore, there are going to be 3 calculations. First, the order doesn't matter, but because we're going in this direction, we're going to be calculating how much heat we need to remove. And you can express that as a minus sign and say, okay, we need to take away this much heat. The order you do the calculations, you can do it whichever way makes the most sense to you. I'll do this one first. So I'll say first, I'm going to cool down the gas to its condensation point. That gets me only to here. Then I have to actually condense the gas and transform it from a gas into a liquid. That will be Q2. Once it becomes a liquid at its boiling point, I then cool down the liquid, Q3, to the final temperature. This means there are going to be 3 heat calculations for problem 2. The first heat calculation will be the mass of the substance times the specific heat of the substance in its gas state times the change in temperature from the initial point only down to its boiling point. I can't go down below its boiling point in the gas state. All right, problem 2 says, I'm giving you the mass, not the volume, of the methanol. So that's nice. I could have given you the volume and have you calculate its mass based on its density. But no, I already took care of that one for you. The mass is 146 grams. In the gas state, liquid methanol is, in the gas state, liquid methanol is displayed as 1,376 joules per kilogram per Kelvin. Once again, we're going to be working in units of joules per gram per Kelvin. There are 1,000 grams in a kilogram. So I'm going to divide this number displayed in the table by 1,000, replacing that comma with a decimal point and saying the specific heat is 1.376 joules per gram. And as before, instead of saying it's per Kelvin, because the scale of a Kelvin, a change of 1 Kelvin is equivalent to a change of 1 degree Celsius, I'm going to display this as per degree Celsius. Down here, per degree Celsius. So that's the value for the specific heat. Now, for the change in temperature, thinking caps on, I'm going to start, my initial temperature is 100 degrees Celsius. My final temperature can only go down to the boiling point of methanol. I go to the chart for methanol, I look up its boiling point, and I see it is 65 degrees Celsius. So my final temperature is 65 degrees Celsius. This means my change in temperature is negative 35 degrees Celsius. That's the limit of how far I can change my temperature and still be a gas. All right, so I plug in the numbers. It's going to be Q1 is 146 grams times 1.376 joules per gram per degree Celsius times negative 35.0 degrees Celsius. I get negative 7,000. Now it says 7,031.36. I'm going to do this to 3 sig figs. So negative 7,030 joules. That is Q1, the amount of heat energy removed from the gaseous methanol to cool it down to its boiling point. Q2 will be the heat energy released by condensing the gas into a liquid. The formula, of course, will be heat energy, Q is equal to the product of the mass of the substance times the heat of vaporization for methanol. The mass is 146 grams. The heat of vaporization for methanol, well, let's see what the table says. Methanol, heat of vaporization is listed as 1.10 times 10 to the sixth power joules per kilogram. Once again, we're going to be working in units of joules per gram. There are 1,000 grams in a kilogram. So I'm going to divide this number by 1,000, which is 10 to the third power. 10 to the sixth divided by 10 to the third is 10 to the sixth minus 3, which is 10 to the third. That means I want to move the decimal point 3 places to the right. In other words, I can replace this decimal point with a comma and think of this as 1,100 joules per gram. 1,100 joules per gram. My calculator displays, it's going to be, now there's no minus sign here, but I look at my heating curve and I say, oh, I have to remove this amount of heat. Since I used a minus sign on the first calculation, I'm going to add a minus sign to this calculation and say, okay, I'm removing, now my calculator displays 160,600. So the 3 sig figs, I'm going to say 161,000 joules is the amount of heat energy I need to lose in order to convert the methanol from a gas state into a liquid state. Next, for Q3, the equation once again becomes mc delta T. The mass is still 146 grams. The specific heat is going to be the specific heat for liquid methanol. We go to the table, we find methanol once again. This time we look up the specific heat for liquid methanol. The number displayed is 2,597 joules per kilogram per Kelvin. Well, we're working in grams, not in kilograms. So by now, you should realize that there are 1,000 grams in a kilogram. I need to divide the displayed value by 1,000, essentially replacing the comma with a decimal point. So the value that we're going to use is 2.597 joules per gram, and a change of 1 Kelvin is equivalent to a change of 1 degree Celsius. So I'm going to write this as per degree Celsius. The initial temperature is the temperature of the boiling point of liquid methanol. The boiling point of liquid methanol is 65 degrees Celsius. The final temperature for problem number 2 is 0 degrees Celsius, and it's still in the liquid state. So delta T is going to be negative 65 degrees Celsius. 0 minus 65 is negative 65. Powering up my calculator, I go 146 times 2.597 times negative 65, enter. And my calculator says negative 24,645.53. And I say, well, the 3 sig figs, it's going to be negative 24,600 joules is the amount of heat energy I need to lose to cool down the liquid methanol to its final temperature. The last result is to sum together these 3 heat energies. On my calculator, 7,030 plus 161,000 plus 24,600, knowing that all 3 of these are negative, my final result will be Q is negative 193,000 joules. Of course, using the Greek prefixes, this would be negative 193 kilojoules. And really, you should practice using them as often as you can.